Papers with code.
Yeah, papers with
Yeah.
code. So like if we select from concept from there,
Hmm.
so what do you, what are we expected to do? So I was thinking of one so let's say took my advanced masters from real-time object recognition.
Okay.
So
I
like
mean,
we
if you're just going to take a YOLO repository and just run that, that's
no,
obviously
I
not
won't do
enough.
that anyways.
Yeah.
Like for example, I'll tell you what I did for DL project.
Uh,
So I did coloring of black and white images.
right. Yeah.
So
Yeah.
for all the repositories I found, all the papers and articles I found was using um, like models like GAN and all, which generates the image.
Hmm.
I did tweak the horizon a little bit, and I used different CNN models to predict the channels and use that channels to from that channels I generated the images using normal Python function.
Hmm. Okay.
So that I used that and I tried using different CNN models, ResNet and
Hmm.
all to compare the result. That was what approach I used there.
Okay. Yeah.
So
I mean, yeah, you can do real-time object tracking or
yeah,
whatever
like
the problem was
is
that
it
you
fine if we
mentioned.
do something like that, like use a different algorithm, like different three four algorithms, and compare the result or
Yeah. Yeah, you can do that. I up added a project proposal document
okay,
on Ubilance. This one. So this has details.
okay,
I guess I should have posted on Piazza. Anyway, I'll
yeah,
talk about it in class
okay,
today a little bit. But I've covered those cases also in here somewhere of like what you should be doing. Uh, yes. So uh, I don't remember where things are. State of the art. Okay. Can adapt a report to a different problem. Uh, that's one way to do it. There's another part somewhere that says uh, comparing an approach on different data sets. That is one way you can do it. Right, yeah. This part here. I mean, ideally, yes, do something functionally different, but
yeah,
if it's a challenging enough problem, then you could um, compare how it functions on different data.
no,
So this is talking about like gluing together a bunch of approaches to do something, not even just using one thing on different data sets and comparing it, because that again, like functionally, it's trivial, right?
yeah,
You just swap out data.
different approaches, all like one all different approaches, and
Yeah. Yeah, either you combine a bunch of things to solve a bigger overarching problem, or um, pick a problem, compare approaches, maybe pick the best parts of each approach and combine them to form something new. Like you know what to do with, since you talked about the, what is it, image in painting
yeah.
restoration. Yeah. Yeah.
question for the project.
Uh-huh.
So in the project, using short algorithm for like object tracking on a conveyor.
Okay.
The concern I face is the data object of conveyor on object. Well, most of it is either have cameras or object move, people moving in subways.
Okay.
So
Why do you want to do
I
that
believe that
particular
that's
thing?
something is in robotics like uh, that information can be fed to robot to find the object that is trying to solve.
Okay.
So that can be further used by the object to manipulate or to change. So that is some information that would be required in the industry.
Hmm.
So
I'm trying to see.
like
There's this in addition to Kaggle, and there's also Papers with Code has a datasets section. Uh, mm, oh wait, sorry, I searched before and after sorting. I don't know, just you could probably go through these things.
so these are images, right? So what I can train on images and
Yeah.
then use that.
Yeah, so then that is a challenge worth uh, thinking about, like how you would scale something that is designed for images to videos,
Tracking is
right? So the naive way to do that would be just whatever your approach is, you apply that to every frame, but then that's not going to be
tracking is
right. I mean, you could still like hold on to whatever predictions you have for each frame, and then
you can map it for different
smooth the trajectory over all frames, but that you won't be able to do that real time necessarily, or at least your trajectories will be noisy since you're doing it per frame. So then, like, how do you deal with that noise? How do you adapt it for a video-based approach? That's a problem worth uh, digging into and writing about in your report.
good industry. What are the like data that people are usually because most of them not industry data like manufacturing data, most of them are like either autonomous vehicles or like facial detection or like people in subways counting things like that. Like is it like a
What's your question again? What data do they use?
common approach now is like people are trying to do with autonomous vehicle and everything. So data set for because I have not seen. I've tried to
They,
look into these.
so
Are,
as
are these not public? So, is that not-
it's not public. I mean, my sample size is not huge, but from whatever work experience I have, generally every product team is very about the idea of using deep learning or ML for stuff, and typically, since there's an audit trail for whatever images are used at all of it is usually stored somewhere by most companies. So, and even if they don't have it structured to begin with, they have the ability to go into like their archives of like documents that have forms with images attached to it, whatever they set up a team to like digitize all of that and structure it, and then that gets handed over to the data science or ML team. Yeah, companies. I mean, there is no incentive to make something that gives them a competitive advantage public, right?
valid enough for project YOLO, YOLO
Uh,
video frame or something like that?
I don't know what DeepSort does.
I think it's same as it's tracking. It's used for tracking objects.
Okay.
And mostly I've seen
Mm.
people tracking cars with their like traffic cam segments.
Yeah, the one, I don't know, just issue that I would have with that is that I've seen that YOLO directly does tracking, I think. Um, yeah, I mean,
I
this
think it's for
this is
object detection.
one of the like highlighted cases that they have for cars, right? For tracking, I don't think they have an example up yet. Uh, text generation. Yeah, they just have that in their image. So, I mean, if they have this, then I'm sure it's been done somewhere. Workout management. Yeah, instant segmentation with object tracking, all of this. So, like, if you pick this up verbatim and just submit this directly, then that's obviously not going to be good enough. I also saw somewhere that they had a newer, yeah, they have a V9, V10 also, but those don't have a lot of documentation or examples or anything yet. This, I think it came out a month ago, month or two. Uh,
Because most of the vision deep learning models are pre-trained,
hmm.
most of them. So like using that algorithm and training my own model would be in itself. I can do a like wrap around that would be easy.
You could fine tune a
Yeah,
model.
like taking YOLO and then using it to detect a certain type of object instead of YOLO can detect everything probably, I guess now.
Yeah, so when I'm talking about fine tuning, if you're using a different data set or whatever, you would freeze parameters for the feature extraction part of the network, and the final classifier at the end, you keep only those weights non-frozen and only update those with a small learning rate so that it adapts to your data set, but the feature extraction part will still remain the same, which is what a pre-trained model does really well. So since you're only tweaking the classifier on a small data set, that shouldn't be a hard um, or it shouldn't be restrictive computationally because you only have to keep track of gradients for a very small number of parameters. And that should be
Match, like not enough.
taking a pre-trained YOLO and fine-tuning it to something else. No, it's got to be more than that.
That that happens with DeepSeek, but this it does. I think.
I mean, you can still do the tracking part yourself. Um, I don't know how DeepSort would fit into this whole thing, since I don't know what it does, but
Simplified algorithm, write it from scratch for tracking. There are many like
yeah, that
naive bases, like mathematical basis of like tracking features across a video, or like
yeah,
multiple frames.
yeah, that would work. So as long as like you're actively engaging with the problem and like you have to think about how best to solve it. That's the objective of the project, right? To get you comfortable with thinking about the problem at hand, what existing solutions are, um, which ones work, why they work, uh, the ones that don't work, why do they not work, and how do you bridge the gap between the two cases, or how do you improve on what exists. And yeah, if you're coming up with your own approach, then
And
that's
compare like how it performs the code.
yeah, you pick something simple as a baseline, uh, see if you can beat that with your own logic, and then if there's something that already is state of the art and you're not able to beat that, that's fine. But as long as you also take a stab at solving the problem, rather than just, you know,
I am. Let's see to how can. Thank you.
yeah. What do you guys think is Saturday too soon for a project proposal, or because I don't expect something very fleshed out or mathematically sound, but just a description of the problem that you aim to solve. So my reasoning behind picking Saturday is that the objective of the proposal is just a sanity check that complexity is sufficient, and what else? Just that you understand the problem that you're trying to solve and have a couple of candidate solutions in mind. Um, and then there's no homework that you're working on this week. So that should give you enough time, I think, to just have a seed of an idea for a project, because next week I do intend to give out uh, another homework, panorama stitching. So that's going to be a bit intense to work on. Uh, okay. Um, so housekeeping things. Let's see. I posted solutions to the quiz. Uh, there's a new section on UV called Solutions. Right now, there's only one submodule within that called Quizzes. I will, okay, really quick. This is what it looks like. There's a couple of questions that I think a lot of people had some confusion with. This it, just go back to the, I think it's lecture 2 slides. And apart from that, the other one that stood out was about Gaussian pyramids. Where's that question? So the arrows by the side are for the right answer. Gaussian pyramid is smaller. Yeah, this one. It seemed like a pretty even split. When we talk about Gaussian pyramids, we have images at multiple scales, but all of them are stored in one array. And since we're having consecutively, the sum of that series, when you keep having the previous term, it's a geometric progression, and it adds up to 4/3. So it's larger than the original. That's about it. The rest I'll leave to you guys to go over. Solutions for the homework. I have the code part done. I'm just waiting for the 3-day 50% grace period to end. So I already posted about this on Piazza, but reminder that for each homework, you have 3 days after the deadline to turn in something that gives you 50% of whatever you would have gotten for that part. And just for the first homework, I'm gonna apply that 50% separately to the written and code parts. So yeah, you don't want to use that in the case where you turned in something on time and let's say you were getting 75%. Even if you do go up to 100 and turn in something after the deadline, the maximum that you can get is only a 50. So if you already have more than 50%, you don't need to use that. But if not, then that's uh, that's some leeway that you have. Yeah, homework solutions, I'll be posting them tomorrow. I'll start grading them tomorrow. I don't know if I'll be able to finish because I also need to prep for class on Thursday, but I will try. The other thing is about the project. So if you want to team up, you can use the Piazza looking for a team post. If you don't, you can work individually, that's fine. On UB Learns, there's a document that outlines the entire project process. I guess I should rename this to just project spec or something like that, because this has to do with more than just the proposal. Please read through the whole thing. Because if you don't, then you won't know what you don't know about what is expected. This is where we're at right now. I could probably push this by a couple of days, but I don't really expect something very fleshed out. No mathematical descriptions expected, just what your problem statement is, how you aim to solve it, and whether you'll be teaming or not. That's and it also doesn't need to be typeset or anything, so just a Word document's fine as a PDF. And after that, so that goes on UB Learns. I've set up assessments. Yeah, so there's this one, and then all of these depend on the previous ones. So I've put in all the dates as they are in the document that I showed you, just so that this is something that's on your calendar when you open UB Learns. I think that's how it shows up. Yeah. There's also a Google form. I believe the link to that is either on Piazza. Yeah, this form over here, just so that I also have a record of what teams you end up going with because this you're free to use this to find someone, but I won't know the outcome whether you actually teamed up with someone or not based on this. So well, I can't do anything about class unless the department or UB as a whole makes a decision about it. So well, so there's what was I talking about? Oh, okay, there we go. Yeah, the Google form. It's just project title and your usernames. That's all I need. That's about Teams, and there was something. Oh yeah, I've also set up a GitHub classroom assignment for that, which there's no rush, but this is the placeholder repo that I want you guys to use for the project. There's nothing in here, but it just makes it easy for me to monitor what everyone's doing. And okay, so for actual class material today, how does everyone feel about machine learning? Is it, do we hate it? Do we dread it? Or are we excited about it? Okay. Yeah, I figured that this is more relevant earlier on in the course today than it has been up to, let's say, a couple of years ago, because pretty much everything now, if you look at the state of the art and the fastest way that things are solved, it usually involves some sort of machine learning or deep learning. So today we'll be looking at some of the basics. What we've seen so far, we've been dealing a lot with pixel values directly. We looked for edges, we calculated gradients, we looked for corners. Those are low-level things that we had to come up with logic for how to do that. So corners, there's no easy way to just look at an image and identify them, which is why smart people figured out that you can think of them in terms of derivatives, and that lets you find them. Similar predicament for the mid-level stuff that we did, which if you think of the case of the panorama stitching example, the whole pipeline involved a lot of logic and clever solutions to find where the right overlap is, what the best transform is to get them to line up. We did that by minimizing distance. There was ransack. So all of that involved a lot of thinking that led up to it. And the reason we do all of that is something we've been talking about right from the first class. We care about describing what is in images. We care about meaning. So that is, we care about semantic information and describing what's in images. Now, it took a whole bunch of time, like 20, 40 years for us to get to amass this like repertoire that has all of these tools that we can use. And reason it took so long is because, well, smart people are in short supply, I guess. And it also takes just a long time to familiarize yourself with thinking about images in those terms, because you also have to know what everyone else is doing, how other people are thinking about images, and synthesize all of that to come up with all of these rules. So it's a collaborative effort and a very drawn out process. We ideally want to speed up that whole thing so that we avoid rules. Now, since a lot of us, or they're ubiquitous now, we have, everyone has a smartphone, there's cameras in pretty much everything. Even our refrigerators are smart now. So there's a lot of data to be collected. Data is abundant. And if we can sort of tease out whatever patterns we're looking for from the data itself, then that lets us circumvent the problem of having to come up with rules. So we let the computers do the thinking for us loosely. But as the problem always is with doing things with computers, we need to be able to represent them as numbers and mathematical operations. So we need to formulate this process of learning stuff from the data mathematically. Now, we love functions, right? A function is something that you give a sample, give an input, and it spits out something, right? So for whatever problem we're trying to solve, if we think of it as a hypothetical function that takes in a sample and gives you whatever you want to know about it, which would be a label, we start off by just coming up with something that loosely approximates what that is doing. And then we pair that with another auxiliary function that lets you estimate how far off of the mark your approximation is from what it actually should be. So we broke it down into two components. There's the actual function that you're trying to mimic, and there's a way to assess how good your approximation is. And typically, these are bucketed into these three scenarios, depending on how much information you have about the type of data that you're trying to represent with the model. You have supervised, which is when for every sample in the distribution, you know what the expected output would be. Semi-supervised is when you only have that information for a subset of the entire data set. So if you have, let's say, 1,000 images, you only know if about 100 or 200 have a cat or a dog or whatever in them. And the rest, well, the idea would be that you use the subset that you have to sort of bootstrap the process of learning about all the samples that you have, and that would extend to the entire distribution. And with unsupervised, well, you don't really have labels of what it is that you're trying to predict, but even though you don't have that, you can still just try to look at the entire distribution as a whole and maybe find some patterns in there. So label for every sample is supervised. Semi-supervised is you have a label for the subset, and unsupervised, you don't have any labels to look for patterns. So we start with unsupervised. I have the word clustering up on here, but even without that, just looking at this, does anything jump out, or do you see a pattern here? Can we do anything with this? Can we think of this as groups of points loosely? How many groups do we see? Just throw out numbers. Okay. Yeah, so there's this one that's very close together, a tight cluster. Then there's another one over here. There's another one that's similarly spread out. And then there's a whole bunch that are sort of just hanging out there. And it would be of some use if we could find a representation that lets us say which group each of these points belong to. So to do that, we cluster our data. And one way to do that is using an approach that's called k-means clustering. The k is for however many groups you're expecting. So we take a sample distribution, and the objective is that we want our whatever is within a cluster should be close to what represents that cluster. So the similar items should all be grouped together, and dissimilar ones should be as far away from each other as possible. Now, there's a bit of a problem with how to start. Like, we need a point of reference to say how far or how close something is. We begin by just picking an arbitrary number of groups based on what we think. Based on what we expect, however many groups it feels like there should be in there, we pick those, and then we pick samples from our distribution. So in this case, we're picking 3, and we use them as our initial centers that represent those clusters. Then for every sample in the distribution, you look at their distances to every other sample in the distribution, or sorry, not every other sample. We look at distances from centers to every sample. And whichever one, so in this case, point A is closest to C1. It's pretty clear from the diagram. We assign each point to the closest center. And what does that give us? Now, there's an issue with what's going on over here that ideally shouldn't be assigned to C1, right? So do we stop here? What can we do with this? How can we improve it? At this point, we have candidate groups, but we still want to refine this. So the reason that the blue point in the C3 cluster got assigned to C1 is because the distance from C3 to the blue point versus C1 to blue point is not giving us the best idea of where it should be. And what are C1, C2, C3? They're supposed to be centers of each of the groups, right? So would finding new centers improve the problem, maybe? Well, one way you could do that is just keep repeating the whole thing, just picking different samples as our centers, right? But that doesn't really guarantee that the next iteration is going to be any better if we're just picking at random. Well, one of the things that we do have now that we didn't have when we were starting out is actual candidate clusters. So what we can now do is we don't have to pick one of the existing samples as our centers. We can just create new centers, which of course wouldn't be inserting new points into the distribution, but we just hold on to new center coordinates. And we get these by averaging the location, just find the center of each cluster and use those to repeat the process. And when you keep doing this iteratively, refining your centers, eventually you end up partitioning your sample space. Does all of that make sense so far? Everyone with me? Okay, so all of this was pretty abstract so far, right? We talked about it in terms of points on, like, this doesn't really mean anything when you think about it. Sure, there's points there, they all have different colors and we group them together, but how does this help us do computer vision? If we had to just verbally describe what's going on in this image, is it a fair assessment to say that there's two colors that really dominate the image? There's a pink, and there's a bunch of green. So if we applied k-means clustering to our pixel values, then, and we set the number of groups that we're expecting based on what's going on in this image to 2, then that gives us a sort of crude way to segment the image. A somewhat more complex image with a bit more variation in how many colors are present. We group this one into 4 clusters and it picks 4 color values, and we're able to use the centers as our new pixel values. So even in this example, once we did cluster all of the pixel values, we then replace those values by whatever the value of our center would be, which is how you end up at this image. Because simply finding the location of the center doesn't let us generate this map. We also use those locations of centers as a sort of lookup table for what our new values should be. So any pixel that belonged to the cluster would then get the value of the center of the cluster. So we talked about unsupervised. We didn't use any labels over that. The only caveat was that we had to supply how many clusters we wanted. For a more defined problem, where you know what value you would expect given an input, let's say it's a simple function that you plug in a number and it returns whatever the half of that number. So if you put in a bunch of values for that and plotted it, then you would get a distribution, something like that. What's going on over here? This, yeah, you could probably think of this as like you put in the it's returning maybe a quarter of whatever you put in. But this is definitely not to scale, it's just for illustration. But let's say your x was 4, you put that in and your output was a 1. So for each sample that you plug in, you get a label. And when you have, so the initial hypothesis that we started out with is that we're trying to approximate a function. So we assume that there's some function that governs how your independent variables or your input maps to whatever the hypothetical function would spit out, right? And what's the simplest kind of function that we can think of? A line going through this would approximate it pretty well, right? Even if all of the samples don't exactly lie on it, they're still pretty close. So whatever your the equation for this line, whatever it is, if you plug in a value there, then that'll give you the corresponding y value. So we defined at this point what we're trying to do. One challenge is, well, a line is kind of simple, and data that we get, you'd be lucky to get something that's very clean and fits to a line neatly. As often is the case when you're acquiring data from, let's say, sensors, those are prone to electromagnetic interference. So that's the acquisition step of the pipeline. Then there could also be errors introduced by just people being part of the process. So I don't know if it happens to you guys, but when I try solving CAPTCHA, sometimes there will be a question like, do you see bikes in there? And well, I grew up calling motorcycles bikes, so sometimes I'll click a motorcycle or a moped or something, and well, that's not really what they expected. So labeling could go wrong. It could introduce bad samples into your distribution, and there could be just some factor that isn't immediately obvious that adds to the complexity of how your points show up in the sample space. So we have choices to make here. There's two factors that we keep in mind when deciding what kind of approximation to make. So bias is an error from whatever the model assumes about the distribution. So a linear model assumes that whatever data we have will fit to a line, but well, in this case, it doesn't fit to a line. So even if you did try to find whatever best line fits this, it might work for a couple of cases, sure, when it intersects this curve at those points, but well, beyond that, that's not of much use. So we pick something that's not linear. We take a quadratic function, and well, we have much better luck using something quadratic in this particular case. Now, well, you'd be inclined to just start off with something complex for every problem then, because even if you do have something quadratic, well, you could just set the coefficients of whatever the higher order terms are to 0. But then this happens. So the higher order your approximation is, the more complex data it can fit. But you don't want it to fit whatever samples you have too well, because then if you add in new data, then odds are that that would no longer be a good enough representation for the entire distribution. And we talk about that sensitivity to variance in the distribution as being correlated with representational power of the model. If you throw a very complex model at a very simple distribution, then well, you're gonna overfit, is what they call it, and that we don't want that. So we want to find a sweet spot of representational power and also simplicity, because if it's too complex, it won't generalize to unseen data. So let's get a bit into the details of how we would fit a line to a distribution. I am gonna get out of here. So, right. We're trying to fit a line to a bunch of points. Now, equation of a line. This one, oh, my bad. Yeah, hide this thing. Well, whatever. So we can represent a line using its slope, which is the A term here, and the y-intercept. If I change the slope of, let's say I start out with just a random pair of values for the slope and y-intercept, and it's somewhere over there. Looking at it, we know that it's not a good fit, and that's because we can see the whole picture, but whatever algorithm we'll be using will only be able to look at individual points and compute some sort of metric that tells how far off from the mark we are with what the best line should be. So I can change the slope and I can change the y-intercept, and we measure how good or bad our candidate line is by computing the distance from each point to the line. We get perpendiculars and just compare the distance. So at this particular line, it's pretty far off, and when I lower the slope, it gets better. When I also lower the y-intercept, now since this is a line, it extends indefinitely. So somewhere about there is where you would find the lowest squared error between squared error of distances. So since the distance is a good metric to tell us how far away from ideal our line is, we plug in a bunch of values for A and B and calculate that and try to find the set of values A and B that minimize this function that computes the distance. And this is generally, this principle is widely applicable, and we'll be using this a lot going forward. Just this way of thinking about formulating the problem in terms of optimizing a function that represents how good your fit is. There's a whole bunch of loss functions, and they're all, a lot of them are tailored to whatever the problem being solved is. So we're not going to get into that right at the moment. Now, zoom in. Oh. So yeah, y-intercept and slope, we fiddle with those until we get a low sum of squared errors between points in the line. And yeah, this just covers the same stuff again. This is just a way to represent that we are trying to minimize the loss function, and the values that we change by doing that is A and B, which is slope and y-intercept. A way to find the best values directly is when the derivative of this loss function is 0. And since we're all dealing with linear algebra at this point, we just set the slope to 0 and solve for A and B, and that gives you the best line. one of the assumptions that's baked into how we're solving this problem is that we are looking for a line. So this naturally has a it has a high bias. And since it cannot fit anything more complex than a line, it has low variance. The good thing about it is since we have the ability to set the derivative to 0 and solve for a and b, there's always a closed form solution. So no matter what your data looks like, you will get a line. Now, that may not necessarily represent your data very well, but you will get a solution. So you're not going to run into a case where you just keep trying out values and your loss just never goes down. It's also fast and low representational power under fits complex data. We already talked about that being a consequence of low variance. Now, another approach, an alternative approach. So here, this is the nearest neighbor algorithm, and well, what we're doing is we have a bunch of points. There's a new point that we want to find the label of. One simple way to do that is just find whatever point is closest to it and spit out the same label. So immediate differences that jump out between this and what we were doing earlier is that we're not trying to fit a line to anything. We're not making any assumptions about what the data looks like, whether it's a line, whether it's a parabola, doesn't matter. It's always going to return whatever is closest to whichever point you ask it about. The trade-off is that, well, it's sensitive to the way all their samples are spread out in the entire distribution. If you have a whole bunch of points, then, well, this gets a lot more involved, and outliers will affect your predictions. It was very easy to just put that out verbally. So implementing it is also not hard. You just have to know where your new point is and just find whichever one is closest to it. And this you can, it's arbitrarily powerful, especially when you have a lot of points. But the trade-off is that if you want to find the closest point, well, with, let's say, 5 points, that's not a lot of computation. But if you have 1 million points and each time you ask it about a new one, it has to compare distances for 1 million points. So it doesn't scale really well. And it takes into account every point that's in the sample space. So it's prone to overfitting in those cases because it will also include those. Whereas when we look at a line, if something's not on the line directly, it still contributes to the process of finding a good fit. But if you have something that's way up top, say over here, well, your slope's going to change based on that point's contribution, but you're still not changing your model too much. Whereas in this case, if you have a point that's like up here, then, well, that also gets included. This style of problem formulation where you have an input that goes into some hypothetical function and spits out a value is called a regression problem. And that is in contrast to classification problems. So if you think of a case where you know a bunch of attributes about patients, I know whether they have a sore throat or not, whether they have a runny nose or not, whether they have nausea, what their temperature is. And what I care about is a diagnosis, whether they have the flu or not. So this is not as trivial as just plugging in a value and getting another value in. So we also care about which attributes tell you, which attributes help inform your diagnosis the best. You could have either binary classification where you have two classes like this one, flu, not flu, or you could have a whole bunch of, say, blood work that's all measuring different properties of blood, and depending on what combinations you have, the diagnosis changes, and there could be many of those, so that would be a multi-class classification. And your variables could either be continuous, like temperature, or they could be discrete. Just you have individual values, like sore throat's a yes or no, and there's no values in between those. The objective over here would be to find a good way to split this sample space along a variable. Now, based simply on the sore throat or runny nose or age, we can't really tell whether someone has the flu or not. But if you look a bit closely at the temperature values that we have in here, there's a pretty neat little threshold that we can find in here. So 99, and it's still not a flu. 98.4 is not a flu, but 99.8 is a flu. So somewhere between 99.8 and 99, if we pick a value and split this data set along temperature, that gives us a reasonable approximation of what cases would result in a diagnosis of flu and not flu. Now we can think of classifying something as a series of conditions, model it as a tree. So depending on what the weather is like outside, well, if it's raining like it was a couple of hours ago, then the only choice you have really is to stay indoors. If it is sunny, however, you could choose to go out. If it's warm, you can go to the beach. If not, then go on a hike. And structuring your decisions like this into sequential choices that you're making allows you to do two things. It lets you partition one at a time, and it's also interpretable. So when you run something through this, you would know how you ended up at a certain class that was predicted. Now, partitioning a sample space, similar to what we saw with clustering, we want a way to divide the entirety of samples that we have in a way that lets us guess what label a point would have based on where it is within the sample space. So we're able to partition based on temperature, which is secondary. Initially, we partition the sample space simply based on whether it's sunny or not. So that's this horizontal line over here. And then on the one side, you have the rainy section, and on the other side, there's the sunny section. So that's our first partition. And then we partition this half again based on temperature, which then allows us to guess what we would do when, in this case, we know that it's sunny and we know the temperature is somewhere about 55. So that puts us in hiking territory. Same thing goes for the other 2 points, resulting in something that looks like this. Is there a problem with doing it like this? There's something too perfect about the kind of data that we have. It's all very neatly clustered, and we already touched on the nature of data in practice. We typically get noise. So while it would be great to be able to partition them very neatly, that's often not the case. So how can we deal with this? We can't say for certain that if this point was a bit closer to say here, well, we don't know what we should be predicting for that. So instead of outright saying what the labels are, we give a probability distribution that says, well, the probability of a hike being the right choice is, let's say, 80%, and then we split the odds 10 and 10 for rainy, for going to the lab or going to the beach. And we do the same thing for every other point that we predict. And that, if you've ever seen the output of something like an object detector, YOLO or whatever, in addition to whatever class of object it predicts. So if you have a picture of a, maybe like a striped cat or something, then you'll probably see like tiger also as one of the low confidence predictions in there. And the way this confidence is represented is, or where they get that value from, is the probability distribution. Putting everything together in context with an example, Viola-Jones face detection is what we're going to be looking at. This is a pipeline that uses a bunch of classifiers and lets us do some cool things, which I will talk about in a second. There's nothing overly sophisticated about it when you compare with what the kind of things that we use for face detection today, where it goes through a whole bunch of convolutional layers in a CNN. There's attention and transformers and stuff. But this, well, Paul Viola, Michael Jones introduced this in, I believe it was CVPR from 2001. It's a classifier that was designed for, with the intent of being used on early smartphones. Well, I don't know if you would call them smartphones, but phones that had cameras. And computational power on that kind of hardware was very limited. So it needed to be efficient. Now, the first problem that the first step for finding anything in an image that we've seen so far is we want features, right? So they came up with an efficient way to find features that is somewhat informed by observation. There's 2 rectangle, 3 rectangle, and 4 rectangle masks that can be applied to images, and these are used to estimate responses and they're called Haar features. Now, what they do with these is something like this. Well, some of the things that we know just based on what you would usually expect from taking a picture of someone's face, especially if it's indoors, there's light coming from above. So the odds of you finding a shadow where your eye sockets are is reasonable. Um, so if you also think about the iris and there's the, what is it, the cornea? I don't know, the white part and the color part of the eye. There's the color part in the middle, and then there's the light parts on the side. So applying these, we're able to sort of formulate a combination that will let us detect faces. Now, the first thing to calculate is the feature response, which is the sum of pixels in the black region um, and the sum of pixels in the white region, and then you subtract the sum of pixels in the white region from the black region. There's another clever thing that they did. Um, they there would have been a lot of computation involved in summing all of these pixels, but instead what they do is for each region that they want to calculate the sum of, uh, you store the sum of every pixel above and to the left in that pixel. So as you go lower and to the right, you already accumulated all the sums of pixel values up to that point, which lets us get the sums of regions in constant time. Great for low computational power sort of scenario. So at this point, we got features, we got feature responses. We need to be able to classify those. So we want to partition our feature space. And this is done using what's called boosted partitions. Now, boosting is you start off by just coming up with a classifier that maybe doesn't do very well, but it's still able to loosely partition your sample space. And then the ones that it misclassified, you increase the weight of how much those samples contribute to the just how you prioritize them higher and then retrain your classifier. And we keep doing this for however many iterations it takes to get to a reasonable approximation. And the final classifier is the combination of all of the classifiers that we get throughout iterating over it. We call the combination of all of those classifiers a cascade. And in cases where the partition is obvious, there are points that are very far on either side of the partition. You don't need to go deeper in the cascade, but the ones that are trickier to classify, we keep going deeper in our cascade until we get to the final one. And since it's structured like this, and for a lot of the cases, you would only have to use the earlier classifiers that lets you make predictions very fast and only spend extra computation on ones that are harder to classify. And when we put all of it together, this is what we get. We're able to find locations of faces in images. And I whipped up a quick little demo of that, which okay. So this is me. This is the responses that I'm getting for hard features. So when there's nothing in there, I wonder, okay, so at this part, there's a bright region, and then there's a shadow in between, and it seems to be responding to that particular pattern if you look over there. And then once I step into frame, the responses change. And there's the integral image part that I talked about. So the sum of every pixel value in the hard feature window ends up at the bottom right pixel, and everything above it is dark. And this will also change a little bit based on whatever features are in there. And this visualization is an aggregate of all the feature window regions. So it could be detecting them in multiple places, but the visualization I have puts them all together. And then, well, does this region contain a face or not is basically what it's saying. And within there, these are kind of hard to see what the values are exactly, but these regions over here, there's definitely no face, which is why you have zeros predicted as labels for those blocks. And then here, those values would be closer to 1. So again, it's spitting out probabilities that there's a face in there. And what does that give us ultimately? I think I have to be looking directly at it, or maybe better lit. Well, I know at some point it should show a box around my face. Yeah, it's doing that. But when I look away, the eye features that it looks for, those go away. So this was a demo of using Haar cascades or the Viola Jones algorithm to find a face in an image. And I'm going to quit out of this. And let me see if I can find what the actual definition looks like. Oh, wasn't supposed to pull that up. See, these are what the actual classifiers are represented as. This does there's the multiple stages up to 25. And you have weak classifiers initially, and these are trees, but they're defined as XML. And each of these values is a weight that corresponds to each leaf in the tree. And there's a whole bunch of those, and these get put together as a cascade, similar to the visual in the slides. Just with a bunch of numbers that's effectively doing something like a series of if-else conditions, we're able to put that together to find faces in images, which I think is pretty cool. And we'll be doing stuff that's a lot cooler than this once we start with our actual deep learning part, which is going to be in a future class, probably. If not next class, then definitely next Tuesday, I'll get there. So as far as the slides and material for today goes, that was it. Now, regarding the project, well, this is something that I was talking to some of you about before class started, but there's this document that outlines the entire time frame, what deliverables are for each phase, and now there's a lot in there. As far as picking an idea goes, the rule of thumb is that it should be a problem that you're interested in, because if it's a problem that you're interested in, then it's a problem that you will enjoy engaging with. And sure, you may have to figure out a lot of stuff. You'll want to pull your hair out probably, but doing is the best form of learning. So just pick something that you think you would want to know how to do by the end of the course. It could be separating background from foreground if you're doing segmentation. It could be learning to detect objects in images. You do object detection. Whatever you can think of is fair game, as long as there is some amount of effort from your side. So what I don't want to see is you just pick an existing repository, just clone that, run it, and take screenshots, put it in a report, call it a day. That's not going to fly. There's the one step higher than that on the effort ladder would be taking something that was designed for, let's say, outdoors images, and you apply it to indoors. Well, you're changing the data set, but the problem statement's not really changing. There's nothing functionally different about it. Whatever you end up doing should demonstrate understanding of the problem that you're trying to solve and the approach that you take. And that becomes evident when you change some part of the entire pipeline, because you can't make a change to something that you don't understand. So if you're able to change something functionally in a way that either improves it or solves a different problem, that is acceptable. Even if you don't necessarily beat the state of the art with whatever it is you're doing, that is still okay, as long as you're able to justify why what you're doing is better than whatever baseline approach you pick to start out. Couple of resources. I guess I'll just share this on Piazza as I do it. I already shared papers with code. There's what do you call it? Data set search. Yeah, there's this, another place to find data sets. So you have dataset search, there's Kaggle, obviously. And you could still aim to do something that's deterministic, rule-based. Going the machine learning, deep learning route is not a necessity, as long as you can justify complexity of whatever it is you're doing. Yeah, there's Kaggle datasets. Papers with Code also has a dataset section, which is useful. And if you are picking anything from here or anything that can be found here, then include that in your proposal. So the tentative, or rather the deadline that I put in for the proposal is for this Saturday. Reason for that is there's no homework that you're expected to be actively working on at the moment. So coming up with an idea and a brief description of the idea and how you aim to solve it with what data. I just a page or two maybe, whatever is sufficient to describe those aspects of your idea. And yeah, just Word or whatever is fine. But the final report needs to be typeset in LaTeX, and there's a template that I've linked to, which you can either use that one or any other IEEE style template. So LaTeX, if you're not familiar, it used to be a lot more challenging to get stuff to compile when we had to do it on our own computers, but thanks to the cloud, we can do it on someone else's computer who already has the environment and everything set up. It's a lot like editing HTML, and we have live, it's easy to find the correspondence between stuff from in here versus what shows up over there when you change stuff. So not too hard once you take a stab at it. And the good part is it looks pretty. So yeah, just read up on this. Let me know if you decide to team up or not. And yeah, that's it. Quiz solutions are on there. Homework solution I'll post tomorrow. Yeah, that's everything. I can take questions if anyone has any.
On someone else's work, or we can like you did that face detector. Could we do something like that, or is that not
The one that I showed
Yeah.
is baked into OpenCV.
Oh, is it?
So apart from the visualizations, I didn't have to do anything extra.
Gotcha.
Ideally, something a bit more involved.
Our face detector, that's the scale of the face in the image. How do you come up with that?
Those masks are run at multiple scales.
I don't think it will be run at different face.
I mean, instead of the mask being upscaled and downscaled, you can do the Gaussian pyramid thing, right? downscale your image and run the mask at the same scale. Under the hood, it probably has all of those optimizations, but the core algorithm is what I covered. The optimizations, well, I haven't like taken it apart and implemented it myself, so I don't know, which is will another case in point for like being the best way of learning. Now, if I'd written that from scratch, implemented it myself, that I'd be able to answer anything about it even like 5-10 years from now, right?
I want the R cascade on the local. Did you attach some instructions to set up and the code on?
Um, I'm I was thinking about whether I should. No, it's not proprietary or anything. Just if I post that, if I share that with you, then that's one less thing I can ask you guys to do for homework, right?
Okay.
um, Panorama. Sorry, say that again.
No, if that's going to be for homework, I think I'll be able to work on it myself.
Okay.
So there will be one less homework.
If yeah, I think I can share that. That'll probably be a good reference for when you're implementing the panorama, not necessarily because they're directly related, but just since there'll be some image manipulation and stuff and just the general workflow, I guess.
Thank you.
Yeah.
Okay, for the project, me and my friend has forming a team, and we thought of an idea, but we're not sure whether it is group, whether it can be done in group or not.
What's your idea?
It's food recognition and calorie estimation. Like, there is an image, will
Hmm.
recognize the food, like object detection of the food, and we'll take that food and we'll calculate the volume, and based on that volume, we'll estimate the. There will be another table called calories.
How are you planning to estimate volume?
Yeah, basically, by identifying the shape, whether it is a sphere or cylinder or
Okay.
something like
Maybe if you could, so until you said the volume estimation part, I would have said no. That's not sufficient. But volume estimation, if rather than just trying to do it with a sphere or a cube or whatever, if you're doing something like say depth estimation, or trying to recover what the 3D structure should be, and then so let's see, with depth, I'm not sure what exactly that whole workflow would look like, but you have an image, you have, let's say, a bunch of, I don't know, what's a good example for foods? Yeah, okay, if you have like, let's say, chopped, sliced pieces of apple or whatever over there, and you apply, so just looking at it flat, well, you could try to find a shape that approximates that, or if you're able to use a depth map or some other method that uh, estimates a mesh of this, then that will give you a volume instead. And then calculating the volume of the object is a question of getting a mask for just that object, which you'll get from your mesh or whatever. And then within that mask, you just sum all the pixel values. So that will give you, but then there's one more challenge to solve, which is what so sum of non-zero pixels within the mask will give you some count of pixels, right? Say 1,000. But if you also need to know the like real world resolution, so 1 millimeter is 5 pixels or something like that, and then um, apply that into this, and that will give you an actual reasonable estimate. So this part would be tricky unless you know what camera you're acquiring your images with. Um, but I'm pretty sure that this problem, like someone would have attempted this. So maybe if you're combining object detection and 3D structure and using that to estimate volume, I think that's something that estimate calories, then that I think would be sufficient for a team project.
Actually, I'll work on today regarding the problem statement and all, and I'll come a detailed report for your office or tomorrow.
Okay.
Can we discuss?
Yeah, I mean, your initial report, I'll be giving you feedback on it. So
So then we can change the project.
yeah, there's a second refined proposal along with the first
Yeah,
progress
yeah,
report
that's
that I
right,
expect.
But for the refined one, we need to just update the existing project that we showed, or we can change the project.
At that point, ideally, you should already have started working on your idea. So preferably don't change your idea altogether. Yeah.
I can come up for.
Yeah. Office hours, I'll be doing it on Zoom only. Yeah. Just call me Varun, man. I'm not.
I wanted to talk to you about the unplanned visit to India. I have mailed you regarding.
Oh, right. Yeah.
So I've actually accepted the assignment on GitHub.
Yeah, I extended the deadline for you.
Until when I can.
You said the 21st, right? Is that still good enough for you?
Yeah, it's enough for me, but you said you'll be releasing that.
Yeah, I mean, you told me what the case is, right? So I won't apply that for you.
So I'll be submitting on 21st.
Yeah. I mean, we are okay with that timeline, right?
Yeah, but I can finish it. I'll try to finish it.
See, I know, like, given the circumstances that you probably aren't functioning at 100%, so
I just came in there.
take the time you need, but just preferably pick a date and let me know what after you think about it, and stick to whatever date you pick. Just email me once you decide.
I'm submitting the written assignment, some contact a mail to regarding that, and I submitted it, a mail to immediately after that.
Yeah, I saw your email. I mean,
That
there will be a deduction. I mean, if you
I
if there was even a single submission before the deadline, then like if you'd gotten, let's say, 80% or whatever on that, like that would.
scanned it way before, but I was doing the coding project, my system crashed, and totally forgot about it. So I just went to
Right.
after that, immediately I remembered, and the system is still not working, so I mailed to someone.
That's not a good enough reason. I can't make an exception.
So do you want me to submit it again, or?
No, I'll consider what you emailed me. That part is fine, but I will be giving you only 50% on the written part. Code, whatever you get, you'll get. Yeah.
We are doing a project for image.
Image captioning. Okay.
We generate a description of what's there in given an image. Is it complex enough for two people? Or
Isn't that just like taking an image and putting it in clip and get?
we are trying to implement a transformer on or we are also planning to extend it to image retrieval. Like we first generate a caption and then we store it using there's something called RAG. We represent it in a.
This is something you've already worked on? captioning on its own is not sufficient. What was the other part you said? Retrieval. Hmm.
web text.
Hmm. Yeah, so that's the inverse problem of captioning, right?
Yeah.
If you have a solution for, if you have a model that works one way, then the same model will work the other way also. Basically, you're learning a joint embedding space for text and images, right?
Kind of multi-model.
If you, mm, can you make this more complex? I guess if you, instead of just, instead of doing joint, because my concern is that you'll just pick something pre-trained like a clip or whatever, get embeddings, and then that solves the problem for you. Um, I can't think of anything to add to it off the top of my head. Oh, there's a problem that I tried working on once. Maybe you could think about it. There was this meme subreddit that I was a part, not even a part of. I just used to frequent that subreddit a little bit, and that sub had a repost problem. Now, reposts don't necessarily have to be the exact same pixel values. Like there's this thing called deep frying a meme, which or like nuking it. So it's still the same image visually. I hope nothing weird comes up. But yeah, so this was an original image that then had a bunch of like filters applied to it that degraded it. Um, okay, nope, I'm closing it. Sorry. Uh, but yeah, um, so the challenge with that is finding a way to see what's in the original image effectively before it goes through all of the modifications, all the uh, degradations that are applied to it, since it's all still the underlying image is the same. So for that, well, um, that's again, if you extract embeddings and check similarity, I guess it's kind of like a biometrics problem. Mm.
With that was we first generated captions, then using the captions theme, we will do that in a vector database. And you can search the vector database to find.
I mean, I think you guys are like halfway there, but think about it a bit more. I don't have any other ideas at the moment. Yeah, just remember to fill the form so that I know.
Project title.
I didn't ask for a title, did I? Oh, just like put some placeholder. Thinking about captioning, just put that for now. Yeah,